Welcome to System to SYS1 Lecture 3B, Combinatorial Logic, where we continue looking at the number crunching units within our system. So in the previous lecture we start to look at how data is represented inside the computer and how we process it within the ALU. So we built up that full adder. So we saw that that full adder was built up of two half adders. So here's our half adder, one there, and an OR gate. So we can build a circuit that can add together 3 bits. So operand bits A and B, and the carry in from the previous digit. Okay, in the last lecture we saw how we could build our logic gates using ladder logic, using relay circuits, and we can now take those logic gates and build our full adder to add together the inputs A, B and C in and generate the sum and the carry out. To show this circuit in operation, I have a video from last year's lecture.
So here we have our circuit, and if I go back to this one here we have the circuit. So I'm just going to go through this one because obviously it kind of relates to what you build in your schematics. So obviously in the old days we used to build our circuits as we do here out of physical hardware. But you'll soon get an awful lot of spaghetti, as I used to call it, these wires joining one thing to the other. So when you're laying out your schematics in ISE, start with your inputs and work across to your outputs. So here I've got my 3 inputs, so A, B, carry in, and my sum and my carry out going across. So you'll look at your schematic and go, or building logic circuit, whatever it may be, and you say, well, I have to build that on the schematic, lay it out neatly. Obviously, when you're designing your processor for the open assessment, you'll be building different circuits. If all the wires are higgly-piggly, you will have great difficulty debugging it, so make sure it's lovely and nicely laid out. There are no marks for presentation in that sense. If it works, it works. But obviously, from your point of view, debugging it can be a pain. So we'll start off with this one here so you can see I've got my A, my B, and my C coming in. So I'll go for my AND gate. So here we've got my signal coming in. So I'll go into my AND gate here. So I'm going through the switches to the inputs. So that one is there. What is also connected to those? Do shout out. So another gate is connected to exactly the same signals. They will be the exclusive OR gate. So the same signal going down. So to my exclusive OR gate down here. So that makes up my first half adder. So this, wrong mouse, this one here. So the output of my AND gate goes to my OR gate. So here we go, we're connecting to my OR gate. The output of my exclusive OR goes to an AND gate. So I've got another AND gate at the top there. My carry in from the previous stage also comes into that AND gate. If you look, wrong mouse again. So there's carry in coming up to that one there. So my second half adder is along there. So I'm taking this one here as my carry in. Goes to the inputs. Same as the other one. So I'm replicating. That signal goes to the exclusive OR to make my other half adder. And finally, the output of my exclusive OR gate goes to the. Oh, should go. Oh, it's the sum. We're building a circuit here. It's not going to work. So it goes to the sum gate there. So what have I done? Have I done that right? Yes. And then so my output of this one here does go to my OR gate. Oh, close call. As you can see, mix a load of wires and me with a sniffly nose, and you get a nice circuit, which is not necessarily a full adder. I've built that. This is your spaghetti that you will have in your schematic. I've built something. So any 1 should give me a sum of 1 on the output. Who's going to put money on this working? I wouldn't. Okay, so 1. Oh, there's 1. Get a 1. Another 1. I get a 1. Oh, we're looking good so far. Any 2 1s should get me a carry. So that's my 1, that's my 2, and I've had both on, that's 3. So I've had 2 1s. Any 2 1s? Oh, yeah, we do. There's a carry. There, and then the final test, the top 2. Yes, we do. And finally, if I have 3 1s, 1 plus 1 plus 1 gives me 3. Round of applause for a moment of cold. Milk that audience. Okay, so hopefully that kind of shows you that we can build circuits that add up using simple switches. So my simple relay circuit there. And the whole point of this one here is just to reinforce, as you're probably learning so far, do lay out your schematics neatly. That will return dividends to you later on when you're trying to debug those circuits. Okay, let's move on.
But now we need to take that circuit and build a bigger adder. We need to build a ripple adder, a circuit that's capable of adding up bigger values. So here we've replicated that hardware 3 times. So rather than drawing out our full adder circuit, which is quite a complex thing to draw out each time, we give that circuit a symbol. So we've got 3 inputs, A, B and carry in, and 2 outputs, carry out and sum. And this is the symbol we use. So the 2 inputs, A and B, the carry in, the sum and the carry out at the bottom there. So here we have 3-bit values. So we've got the value A and B. So you can see we've got A0, A1 and A2, and B0, B1 and B2. So, and we have our output, which is a sum, which is again a 3-bit bus. So we've got sum 0, sum 1 and sum 2. And we've also got a carry out here. So we can see that circuit in operation now. So we'll add together 2 values, 7 plus 1. So each of the full adders implements the addition of a column of our number. So here we've got our 3 columns, which are 3 bits within our number, and each one of those is processed by a separate full adder. And obviously the carry is being generated from one digit to the next. Is the carry out and the carry in path you can see there. So we apply the values. So you can see our A is all 1s, so all the value 7, and our B is the value 1, so 0, 0, 1. So here's our A, least significant bit, so 1, 1 and a 1, and B 1, 0, 0, and we're going to add those together. So starting at the least significant digit, so you can see obviously 1 plus 1 gives us 2, so 0 and a carry. Now the next digit, so we've got 0 plus 1 would give us a 1, but got carry in, so it again gives us 0 and a carry, and the same for the last one, giving us 0 and a final carry out. Okay, to see if that made sense, a quick quiz. So what we have here, we've got 2 octal numbers, so 2 base 8 numbers. What I'd like you to do is to convert those into binary, so 151 base 8 will go in there, and 252 base 8 will go in here as binary representations. Then add those binary numbers together to confirm you get this result and these carries, and then convert the binary result into the final octal value, 423 base 8. If you'd like to check your answer, my solution is on the module webpage. One thing to note for this circuit here, the carry out obviously is the 4th bit, but it's used in the system more as an indicator that an overflow has occurred. The calculation exceeded the internal representation that the machine is using. So in this example here, we've got 3-bit values. So if we generate a 4-bit result, then we've exceeded the internal storage capacity of the machine. We can only store, in this example, 3-bit values. So 4-bit one, we need to test for that, and that's what the carryout allows us to do. So when that line there goes to 1, it indicates that we've got a problem. We've generated a number that's too big to fit into our system. So in the simple CPU, it's an 8-bit machine, so the carryout would indicate we've generated a 9-bit result that can't be stored in the 8-bit internal general purpose registers, the accumulator. Another thing to keep in mind that is obviously I kind of inferred a sequential behaviour when I was describing the previous circuit, but that's not how the circuit will actually work in reality. So obviously each of these full adders is a piece of hardware working in parallel, working at the same time. So to show that one in action, let's reconsider that value again, so 7 plus 1. So now if we apply the values here, because of the internal construction of the full adder, the sum value will update first because it has only 2 logic gates in its critical path. So if we look at this one here, you'll see 7 plus 1 will give us obviously the temporary or transitory output of the value 6. But then the carry from the least significant digit will propagate through to the next adder. So this addition here, which obviously will cause this one to flip from a 1 to 0, generating a carry to the next stage, as you can see here. Again, that 1 there will cause this the most significant bit to again be updated from a 1 to a 0 and generate our final carry out. So the thing to note here is that the outputs will go through some transitory states, but finally settle down to a final stable value. And obviously that's determined by the critical path of our system, how long it takes to settle. No escape, another quick quiz. Can you tell me what the critical path delay is for this 3-bit ripple adder? So what is the worst case delay from the inputs changing to the outputs reaching a stable state? Remember, in each of these full adder symbols is this circuit, and from that you can work out what the worst path is. I should warn you, it's perhaps not as easy as you think. There's a slight twist in the solution. You may want to pause the video now as the answer follows. The thing to remember, obviously, the critical path delay for a full adder is 3 logic gates. So you can see here the signals come in, so it's 1, 2, 3. But that's only true for the first one. Obviously, as this hardware is working at the same time as this one is, this logic gate here, which forms part of the critical path delay, will have updated to the next value. So the full adder here, the XOR will be stable by the time the carry comes in. So the critical path delay for each of the subsequent full adders is just 2. So the signal comes in and it'll pass through 1, 2 logic gates, because this obviously XOR gate is stable by the time the carry bit gets to it. So you've got 3 logic gates delay for this full adder, then 2 gives me 5, then another 2 gives me 7. So 7 logic gates delay, or if each one takes 10 nanoseconds, 70 nanoseconds before I have a stable final output. As always, there's an IC project to help you work through the Ripple adder. So on the module webpage, there's a zip file adder_8, which contains an 8-bit Ripple adder we'll be using in the processor. You can simulate the operation of this adder via its test bench, as shown by the waveform diagram here. This applies a series of 8-bit values onto the A and B inputs, as you can see here. So you've got zeros there, then it goes to 1, and these generate a result on the sum and the carry. So you can see here, we've got 0 plus 0 gives us 0, 0 plus 0 plus a carry in gives me the value 1. So do make sure you go through these IC projects, because it'll give you good experience for the open assessment. So open up the top level schematic, you'll see this symbol here, and push through the hierarchical schematics until you finally get to that half adder. Just before we leave this slide, another good test to see if you understand what's going on is, does this waveform diagram make sense? Can you see, for example, why the carry out goes high at this point? Okay, so we're heading towards now building our ALUs, but the ALU does more than addition. It does obviously subtraction, some logical operators as well. So how are we going to implement that in our system? How do we tell this ALU what function to perform? Well, this is the symbol for the ALU. So you can see I've got my 2 8-bit values coming in and our 8-bit result going out. And we've also got an extra bus coming in, the control bus coming in, which tells the ALU what operation to perform. So each operation is given a command code. So you can see here the 3-bit value. So if it's all zeros, I do an add. If it's 1, I do subtract. If it's 2, I do a bitwise AND. We'll look at that in a little bit. If it's 3, it's not used. 4, I pass through. I think it's result B to the output. So just a pass through, not affected. And the others, again, not defined at this time. So if you look at those functionalities, some of those we can do already. So pass through, as we've got here, just passing, selecting a particular input. So selection, that's a multiplexer. The addition I can do with a Ripple adder, but how do we perform the subtraction and the bitwise AND operations? That's what we'll have a look at now. So subtraction, well, first before we understand what hardware we need, we understand what process we have to go through for subtraction. Again, some people struggle with the binary subtraction, they get confused, but again, just think, how would I do it in decimal? And it's exactly the same process. So we'll start with this example. So obviously got 0 take away 0 gives me 0, 1 take away 0 gives me a 1, 1 take away 1 gives me a 0, 0 take away 1 I can't do, so I have to borrow from the next digit as you would in decimal. So borrow a 1 from there, obviously it's a power of 2 difference between the 2 columns here, or the 2 digits. So when I borrow 1 from there, it becomes 2 when it moves into this one here. So I have 2 take away 1, which gives me 1, and that obviously goes to a 0, so I've borrowed 1. Another way I think of it is the block method. So you can look for a block of digits. So you start with a 0, looking along until you get to your first one. You then replace that with, basically you invert the bits, so it goes 0 and then all 1s, and continue the subtraction, putting 1 in the result. So again, if you took that as your block, you look along, so there's our block inverted, so that goes to 0, that goes to a 1, and then put a 1 in result there. But I like to think of it as borrowing a 2, so that goes to a 0, so it's 2 take away 1, gives me 1, and that obviously goes to 0, so same result. Now we've got 0 take away 0 gives me a 0. Again, I've got a situation where I have to borrow, so I look along, so I borrow 1 from there, that becomes 0, so that becomes 2, borrow 1 from that, so that's a 1, there's a 2, 2 take away 1 gives me that 1, turning that 1 into a 1 there. Then 1 take away 0 gives me a 1, and 0 take away 0, so my final result, 150 minus 44, gives me answer obviously 106, or all in binary 11011010. So for that previous example, I chose a result that would generate a positive result, but obviously if we do subtraction, we could generate a negative number. So the question now is raised, how do I represent negative numbers in my system assigned values? Different ways of doing it. So if you may want to look into your own time as signed bits, so you can use just one bit to indicate if a number is negative. But the method we're going to use is 2's complement to represent our negative values. So what you do here, you can sort of see an example here, we use the most significant bit to represent whether the number is positive or negative. If that most significant digit is a 0, then it indicates a positive number. If it's a 1, it represents a negative number. Another key thing to remember is that most significant bit no longer represents numerical value. It is an indication of the sign of the number. The reason we do like to use 2's complement is it allows us to reuse the same hardware. We don't need to design special hardware as the signed digit method would need us to do. Okay, so you can see here we go counting up, so it's 0, 1, 2 and 3. Obviously you can't represent the value 4 because that would need to use that most different bit, and as I said, using signed numbers, it represents the signed digit now. One thing to note, in 2's complement you always represent obviously one more negative value than you do positive, because obviously 0 technically is a positive number using 2's complement because it's obviously got a 0 in the most significant digit position. To convert from one to the other, from a positive number to a negative number, all you have to do is invert the bit positions and add 1. And to go the other way, from assigned to unsigned, again invert the bit positions and add 1. So here we have some examples. You can see this is a positive number, so it's positive 1 because the most significant digit is a 0. So to convert this to -1, all we have to do is invert the bit positions. 0s goes to 1s, 1s goes to 0s, you can see there. And then we add the value 1. So we perform the addition of +1 to the number, whatever it is. And that gives us a result, all 1s, and all 1s is -1. Another example, you can see again 100 into -100. So again, it's a positive number because the most significant digit is a 0. Again, invert the positions, so 1s goes to 0, 0 goes to 1s, and then add numerically 1 to the final results. Do remember though, obviously by giving up one of your digits in your binary representation, you fairly half the range of values you can represent. So in this example here, where I want to represent the value 200, I can't convert that to -200 because I need to use that 8th bit, bit 7, to represent 128 when I do that conversion into binary. So therefore, if I try and convert that into -200, I'll get the wrong result because obviously that most significant digit is not free to be used as a signed bit. In those situations, obviously, you have to add extra digits. You have to extend that number to a 9-bit representation rather than an 8-bit representation. To go the opposite direction, so from -100 to +100, again, just invert the bits and add 1, and it's the same process. When you're performing addition of signed numbers of different lengths, so you might have 8-bit values or 16-bit values, you sign extend. So here we've got the values -100 and +100, so you can see again minus, most significant digit is a 1, +100, the most significant digit is a 0. So if I want to convert those to 16-bit values, I have to extend the sign digit. So for negative values, that means replicating the 1s. So there's the 8th one there. You can see I've just replicated that 1 all the way up to make it a 16-bit value. And obviously if it's a positive value, I replicate the 0s there. So again, the key bit here is it doesn't matter what the size of the number is, the most significant digit has to be the signed digit. So that's why you replicate the signed digit when you sign extend. As always, to check to see if you understood that, we have a quick quiz. So here, what I'd like you to do is perform the subtraction of these hexadecimal numbers. So you can tell these are hexadecimal numbers because they start with 0x. So 0x for hex, and then our 2 hexadecimal characters. So convert these 2 base 16 numbers into their binary representations, and then perform the subtraction, confirm that you get the result here. Also make sure you can do the subtraction working in base 16 rather than in binary. So perform the subtraction as you would do with decimal, but that's obviously working in base 16. So here we've got 10 minus 12. Obviously you can't do it, you have to borrow 1. So what do you borrow? Do you borrow 10 or do you borrow 16? So as we can see here, this generates a negative result because the most significant digit is a 1 in our 2's complement representation. So just to confirm that this is producing the right result, you can convert these hexadecimal numbers into decimals. So the 2a is 42, so 6c will be something. And you can see here we're converting the negative value into a positive value by inverting the bits and adding 1. So the answer should be -66 base 10. As always, my solution is on the module webpage. So what hardware do we need to perform this subtraction? Well, the same as addition, we've got a half subtractor and a full subtractor. We could build it out of logic, but that would mean doubling our hardware costs. We need an adder plus a subtractor. So what you typically see in a computer is that we reuse the adder, but we perform subtraction through the addition of a negative number. So we took our example here, we have subtraction previously. So rather than subtracting 44 from 150, I can add -44 to 150 to do that subtraction. So rather than a minus b, I can do a plus minus b. So you can see the 44, what I've done, I've converted that to a negative value. So I've inverted the bits and added 1. So it gives me my minus 144 as a 2's complemented signed representation. And now if I want to do the subtraction, I just add the 2 numbers together as I would normally. So 0 plus 0 gives me 0, 1 plus 0 gives me a 1, 1 plus 1 gives me 0 and a carry. 0 plus 0 plus a carry gives me 1, 1 plus 1 gives me 0 and a carry, gives me 1, and then gives me a 1, 1 plus 1 gives me a 0 and a carry, 0 and a carry. Now the key thing here is when you perform signed addition, the final carry is garbage. It does not represent an overflow. So do keep that in mind. So when you do signed addition and you get a final carry out, just ignore it. It doesn't represent the overflow in our calculation. So for signed arithmetic, we have to use these rules here. An overflow is detected when you have a change of signs. So if we have a minus b, or minus a plus b, or plus a plus minus b, the magnitude of the result will always be smaller. In those situations, obviously we won't generate an overflow because we're generating a smaller result. Here, where we have a plus b, or minus a plus minus b, we could generate a bigger value. Therefore, we need to check that the signed digits match our operands coming in. So obviously, a positive number plus a positive number should generate a positive result, or a negative number plus a negative number again should generate a negative result. You can see that when we have a look at these examples here. So here, where we add together two numbers, so a positive number and a negative number, we know there's no problems because obviously the result will be smaller. Here, where we have a positive number plus a positive number, we do have to check that the sign bit of the result matches the operands coming in. So when I add together two positive numbers, I should obviously generate a positive result. But because I'm generating a result that is generating a signed overflow, the result sign bit does not match because obviously it needs to use that bit position to represent numerical value. So 255 plus 1, obviously that's the bit 8 position, the 9th bit, to represent 256 obviously. So here we have generated an overflow, and we can detect that overflow because the sign bits do not match. Okay, so how we build our adder-subtractor unit in hardware? Well, what we can do is, as I said, we use the same adder circuit, the same ripple adder we saw previously, but we just need to now invert and add 1 on one of the operands coming in. So the way we can do that one, you can build it out of a multiplexer and an inverter circuit, as we saw in the labs. Or another way of building that is to use an XOR network. So this XOR gate here takes 8 inputs and XORs each one of those individually with a common term coming in. So if you look inside that component here, you have this one here. So you can see you've got an 8-bit bus coming in. So each one goes to a separate exclusive OR gate, and then it's XORed with the same B signal coming in. So if B is a 0, if you XOR the signal coming in with a 0, then it's basically passed through unaltered, because if it's a 0, you'll get a 0. If it's a 1, you'll get a 1. If B is a 1 and you XOR your signal coming in, then it'll perform the inversion. Obviously, if this is a 1 and that's a 0, you'll get a 1 on the output. And if that's a 1 and that's a 1, obviously you'll get a 0 on the output, inverting whatever that each bit is on the output bus. So that performs half our steps of our 2 complemented representations. So I've inverted all the bits by using the exclusive OR gate. Then I need to add 1, and obviously a nice easy way of adding 1 on our ripple adder is to use the carry in, because the carry in is not normally used in unsigned arithmetic, but here we can set that to a 1, and therefore that would be a carry in of 1 on the least significant digit, i.e. you add 1 to the value going in. So this is our adder-subtractor hardware. So if the control signal coming in is a 0, then obviously carry in is 0, so don't add 1. 0 goes into there, it means that the B input is, the B operand is passed unaltered. But if the carry signal is set to 1, then the carry in is 1, so I perform my add 1. And if it's a 1 on there, I perform the inversion. So therefore, the hardware actually performs the subtraction. So that is the adder-subtractor functionality built in hardware, but also we need a pass-through and bitwise AND inside our ALU. So if you look inside the ALU, there's not an awful lot in there. So the thing that selects what functionality the ALU does is a final multiplexer here. So if you can see the control signals or the select lines of the multiplexer select either the adder output, or this one here turns that adder into a subtractor, so it's still on the first input. The second input, the B input, is the bitwise AND, which we'll look at in 2 ticks, and the third input, the C input, is just a pass-through. So whatever's on B is passed through unaltered onto the output there, and that's used for moving data around or loading data from memory where you don't want to actually change the value. So we've got adder-subtractor, bitwise AND, and pass-through, and that's all that's in the simple CPU's ALU. Very, very simple. The bitwise AND function is performed on the 2 8-bit operands coming in, so A and B, and this circuit implements that functionality. So all you're doing is for each bit in the 2 values coming in, you're performing the bitwise AND to generate the result going out. Where there's a 0 in one of the operand bit positions, obviously you'll generate a 0 on the output result. So it's only when you have a 1 and a 1 in the same bit position that you'll generate a 1 result. So 45, which is that value there, 198, that value there, added together gives you a 1 at bit position 2. Again, do keep in mind that there's no way of telling whether this 8-bit value is positive 198 or signed minus 58. Again, most significant digit set to 1 there. The same bit patterns represent both values, but you as a programmer know what value is stored in each memory location, so you know if you're storing a signed or unsigned representation. But just looking at the raw bit pattern, you cannot identify that it's a positive or negative number stored at that location. At first glance, you may think bitwise AND operations, why would you perform these operations? We'll see later they're quite useful in masking out selecting particular bits in a number. For example, if you want to see if a number is positive or negative, you're only interested in the most significant digit, and you can use a bitwise mask to select that digit. And finally, we have the 3-input multiplexer that generates the output of the ALU. So if we go back and look at the ALU schematic, so that's the symbol for the 3-input multiplexer. Each of its inputs is an 8-bit bus. So to implement that, we take our standard 2-input multiplexer. So in this component here, we have 8-bit multiplexers, multiplexing each bit of the 8-bit bus. And combining these together, we can make a 3-input 8-bit multiplexer. Okay, to sum up, we had looked at some binary arithmetic. We saw we could take our full adder to make a ripple adder. We saw how we could perform subtraction, represent negative numbers, and implement our ALU. Okay, I think that's where I'll leave it there, and I'll continue in lecture 4.